Hello, everyone. I'm Tao Wang. I'm here to introduce our work, SynSP, Synergy of Smoothness and Precision in Pose Sequences Refinement. Using existing human pose estimation algorithms to estimate human pose sequences often encounter various errors. Human motion refinement algorithms aim to optimize human pose sequences from pose estimation algorithms while ensuring minimal computational overhead and latency. Previous works have focused on the balance between two task objectives, smoothness and accuracy. However, we note that the tension between these two objectives can provide additional confidence cues about the predicted pose sequence. In turn, these hints are able to help the network optimize low-quality human poses. To exploit this quality information, we propose a motion refinement method, SynSP, to achieve the synergy of smoothness and accuracy in the task of human motion sequence refinement. Let's look at the relationship between two task goals, smoothness and accuracy, and confidence. A human motion optimization algorithm has two losses, precision loss _P and acceleration loss _A, which are used to supervise the human pose joint point position and joint point acceleration, respectively. So we can adjust the weight ratio of these two losses to make the network focus on accuracy or smoothness. The horizontal axis of Figure 1 represents the loss-weight proportion, and the vertical axis represents the PAPE error, accuracy error, and accel error, velocity error. At the positions of 0.5 and 5 on the horizontal axis, the network output is respectively biased towards smoothness and accuracy. At this time, we can obtain the difference between the two outputs, represented by the blue line diff2 in Figure 1b. We can also obtain the difference between the estimated human pose sequence and the true sequence, represented by diff1, which represents the true input error. It can be seen that diff1 and diff2 have certain correlation. We calculated the Pearson correlation coefficient between diff1 and diff2 on the human 3, 6M and 3DPW datasets. Based on our experiments, the average of the Pearson correlation coefficient is 0.48, considered as related if greater than 0.3, indicating that the difference between the two output sequences with different emphases, diff2, can serve as an indicator of the quality of the predicted sequence without knowing the true value. We use the transformer structure to process temporal sequence information, mainly composed of two stages, base stage and refinement stage. First, under the guidance of pose similarity encoding I, the base decoder can generate two branches simultaneously using both individual and global information, with a bias towards smoothness and accuracy. Then, these two branches can generate pose quality encoding, as well as a more precise, pose similarity encoding II, which further helps the refinement decoder generate optimized results. Pose similarity encoding. Pose similarity encoding calculates the similarity between multiple poses in the input. It mainly helps with assisted localization in multi-view situations by using similar poses to refine the current pose. Additionally, this encoding also reduces the attention paid to incorrect poses. Base decoder. We parallelized the last layer of the base decoder to output to decoder layers with different emphases to produce optimized pose sequences for generating confidence information. Refinement decoder. Pose similarity encoding can be further optimized by the optimized pose sequences produced by the base decoder. We guided the attention of the refinement decoder using pose quality encoding and optimized pose similarity encoding II to refine the sequence further. SynSP achieves state-of-the-art performance with an input length of 8 windows in multiple datasets, while current methods typically use window lengths of 32 or 100 plus. Additionally, SynSP accelerates the processing speed of some algorithms through parallel computation, significantly reducing the delay in post-processing. SynSP utilizes confidence information to achieve state-of-the-art performance in the field of human motion refinement with the lowest latency and smallest window length. Besides this field, most tasks currently have optimization targets with certain conflicting relationships, where the network can assess the confidence level of the input data and use this information to optimize the output, which is also our exploration direction in the future. Thank you.